through and stopped at Petri nets, and the idea was that you will look at everything else related to the discrete event models, namely building examples of models with Petri nets and reachability graphs, right? I'm not sure if you have reached reachability graphs, but sort of let's assume that you have. My plan for today is to show a couple of examples from this building blocks lecture. So the whole talk is pre-recorded, it's long, but I will just open a couple of examples from there. Why? Because they are fundamentally very important. One of them is a pipeline, the other is an arbiter. And then after that, there will be examples of modeling, and we will try to sketch the solutions to the problems, and the problems are formulated in the slides. So that's what I'm trying to do. Reachability graphs. Reachability graphs is something to discuss as well, and actually there are several illustrations here in this JPG pictures. It's those which I sketched by hand, and I will just, well, the commentary is in the talk over here. So I will just ask you questions about how it went with those reachability graphs, and clarify a few points if you ask questions, and if you don't ask, then we'll see what to do. Right, so building blocks for models, modeling with Petri nets. Modeling with Petri nets, sharing this. View is correct. So in the previous material, we had the definition of a Petri net. We had some rather basic examples, and those examples were illustrating the concept of a Petri net. And then there was one example, the very end, which was fundamentally very important. It was about a handshake principle. So when processes communicate, it is important not just to give a command to the other process, do something, but also receive a feedback, a response from there. Yes, I've done. It's acknowledgement. If this acknowledgement does not come for some reason, then in case of repeated and cyclic operation, a problem may occur. It may happen that you may overload the slave device with tasks. So you need to wait until the previous task is finished. So for this, we need some sort of a feedback. Right, so there will be more examples here, and let's have a look at them. So I start usually with fork join building blocks, and later on there will be a choice merge. Similar picture, and after each of such slide there is an example. Why I separate them as fork join and then choice merge? Because fork join is dealing with concurrency, and choice merge does not deal with concurrency, but rather it is about functionality which is very well known to us from finite state machines. Let's not talk about the second couple. We'll start with this first couple of operations. Fork join. So we're going to look at the structures which look like this, this, and that. So this operation is fork. So the idea is that fork happens when the central operation is a transition, right? When this transition fires, it consumes from the preset, which is this place, consumes the token, and then places tokens into the post set here, here, and there. So one token disappears, and in this case, 3 tokens appear, you see? And then you can attach to each of these output places a thread. And then this thread will start once the token is placed here. This will start, and this. So basically, it is an operation which starts several threads upon execution of this transition. Does it make sense? Of course, this transition cannot fire without a token here. So I'm saying that this is just a building block. So to this building block, we need to connect something on the left and connect something on the right. That's what I mean by this model. So the idea is that the fork starts concurrent processes and increases concurrency. In this case, one thread comes in and 1, 2, 3 threads come out. If you want to produce 10 threads, okay, draw instead of 3, draw 10 arcs here, and there will be 10 places here, right? And thus, by execution transition, you will launch 10 different activities. Well, in software engineering, so we will be using an operation pthread create, creating a thread, right? And then pthread create creates just 2 threads. Basically, one thread is where the command is included, and the other thread is the new one, which is created. So it will be a smaller fork compared to this, but still very similar. Now, join operation. Join operation usually goes hand by hand with a fork. What it does, it reduces concurrency. How it works? So to this, and these places, there should be some nets connected on the left, right? And each of those is a thread. And when the thread is finished, it puts a token here. When the second thread is finished, puts a token there. And the final thread is finished, puts the token here. And only when all three places are filled with tokens, only after that, this transition becomes enabled and fires. In the process of firing, it will eat the tokens from here, here, and there. So it will consume them and will place a token there. So on the right, there will be another net connected. It will be just one thread. So we are finishing 3 threads, waiting for all threads to finish and start anew, right? So this is join operation, and join operation is usually associated with waiting for the threads to finish. And we will have in software, I will have a join command which waits for a thread to finish. Right. Now we can have a combined operation, fork and join. Basically, it's a hybrid between the two. So we can have several threads joined at a transition and then several threads forked from a transition. Right. So if necessary, we can just change the amount of concurrency by doing this, or we can have, for example, 3 input threads and 3 output threads, and then this transition still makes sense. What sense does it make? It will cause the system to wait for a perfect alignment of tokens here, and then it will produce firing and everything will be relaunched. So this kind of waiting, it's for the purpose of guaranteeing that the system goes through some particular marking, through some particular state. So if you need to register this state and undertake some action, you can have it. So in general, the purpose of this fork join is to manipulate concurrency and, first of all, to create concurrency. And concurrency is needed for less synchronization, more freedom, and fast operation. Why is it faster? Faster because if we are not waiting for another party to finish, then without waiting, hopefully the system will run faster. So it's common sense. Fork and join. Note that if you have a fork in your system and the system operates in a busy cycle, then you must have join somewhere. Why? Because otherwise you will be increasing the number of tokens. It will be more and more and more and more. And eventually the number of tokens in your system will be the same as the number of places. And there will be no more space to store the tokens in one safe network, right? So usually in a cyclic system, you have forks and joins combined together. Doesn't make sense. I can still hear those beep, 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 and someone makes noises with dishes probably. So if you need to cook something, could you please mute your microphone? But otherwise, please feel free to keep it unmuted. Now that's the illustration, and I want to add quite a few comments to this illustration. It is an animation, and I can quickly show how it works. Something is there, and the green arc is moving. But what does it mean? Rewind to the beginning. Rewind it back. Right, so it's a Petri net, and I call it a pipeline model. A pipeline consists of stages. 1 stage, 2, 3, 4, 5, 6. Well, let's ignore this stage and this stage because they're incomplete, because they're different from what we have in the middle. Okay, so let's say that inside the pipeline we have 1, 2, 3, and 4 stages. Who is making this beep sound? Could you please stop doing this? So each stage includes 2 places, this one and this one. And this one is interpreted as the stage is empty, and this one is interpreted as the stage is full. There is a token in the loop for each stage. And if this transition fires, then the token disappears from here, appears there. If this transition fires, the token disappears from here, appears there. And there's a general rule that in a loop, any loop in a Petri net, if there are no choice and merge operations, just those transitions like fork join, then the number of tokens stays more or less consistent. Yeah, well, of course, you can sort of split it and have this fork and more here, and then they will be merging, but that's what I mean by more or less consistent. So the token just runs in circles and marks either one place or the other place. Now let's interpret those places in a very simple way, and it helps to do hand waving. When the token is below, then I say, well, my arm is down or the flag is down, and this place and this stage is empty. When the token is there, I raise my hand, flag is up. It means that the stage is full. The token itself, it is just a flag which shows the state of this stage. It's not really the data item. It's not the data item which came from the left and now placed here and goes further. We can imagine those data items, and the green arrow in my drawings, it shows this data item which is propagating from one stage to the other, but the data item itself is invisible. We can only see those flags which are going up and down, and they're showing whether the stage is full or empty. Right? So at the moment, this stage is empty, this stage is empty, all of them are empty here, right? The input interface, it's half of the stage. Apparently, the interfaces are also stages of a pipeline. But let's ignore it for now. So the input interface is full. Now look, which transitions in the system are enabled? This one is enabled because it's preset according to this arc and this. It's preset, so this place and this place is filled with tokens. So this transition is prepared to fire, and this corresponds to the data moving from this stage to the other stage, and the flags, this flag will go down and this flag will go up. Why? Because if you fire this transition, then this and these tokens disappear, and the tokens will appear here and there. Does it make sense? Everyone says yes.
Yep. Yes.
Now, once
Yes,
again.
Yeah.
Thank you. I was not forcing it. I just kind of talking to myself because I couldn't hear anyone, and thank you for responding. Now let me do this first step of animation, and yes, exactly the same thing happened. Now this flag here is up, so the stage is full. This stage is empty. As this stage is empty, then nothing will come from here. It's empty forever. But this stage is full, and according to the discipline of what we mean by saying that this is a model of pipeline, this stage should move its data further, according to this green arrow. And it will happen. Why? Because this transition now is enabled. Because of this guy and this guy, right? This transition is enabled, it will fire, and as a result of firing, this token will go down and this one up. So it means that the data has moved. Now the flag is here, goes down, and this one goes up. So exactly that's what we will see. Like that. What happens next? Well, the same as with this guy. What happens next? The same as with this transition. Nothing is coming from here because no input here. You see, I don't have any path from empty to full state. Therefore, I only launched a single data item to roll along the pipeline. And of course, it rolls along, and eventually it cannot escape, right? Why? Because we have a stopper here. It's the interface which is similar to this one, just at the bottom there is a token missing. And as a result, this transition will not fire. And the data item which moves along, it will become stuck in this stage. Become stuck means that there will be a flag here, which is full, and a flag here, which is empty, like that. And that's it. The first experiment is over. It's a dead end. Nothing will happen after that. They call it deadlock. Deadlock. After that, nothing happens, and the operation of the model is finished. The next slide will be a new model. I emphasize this, and those who do not understand it, shout at me in frustration, please. The next slide is a new model, very similar to this one, but a new one. Why? Because I am putting a new data item here. The model, it's the structure of the system with all data in it. But if I'm modifying something, either the structure of the system or adding a new data item there, then becomes a different model. Right, so the different model. The different model is, we have the same from the previous experiment, the data item sitting here, the flag is up, and the new flag is up here because a new data item is launched. What we will see now, this data item, it will roll along the pipeline, but it will refuse to merge with this one. Why? Because if this flag is up, then it's not down. It's either up or down, not both. If it is not down, it means that there is nothing here. It means that this transition will not be enabled, and means that this data item will roll along and become stuck here. Right? Okay, let me play this animation like this. Going further, further, and becoming stuck. You see? Now nothing will happen with this model. No activities are enabled, therefore it's a deadlock again. Now let's continue our experiments. Just the next slide is a new model again. Why? Because I will add something to this. I will raise this flag here, so I'll launch another data item. Well, a similar way as I did before. And at the same time, I will unblock the output interface. And some data items will start escaping from this side. Why I'm doing this? I'm doing this because you will see that in a pipeline, several activities will be happening. So this data item will be rolling along. And from this side, some data items will be escaping. And a lot of switching of flags will be happening. They're going up and down, and you will see that this system is massively concurrent. It's quite complex. Before that, it was a simple operation because things were happening one thing at a time. But now you will see proper concurrence. So this is my modification. So I have added a data item here, and I unblock the output. Look, this data item will try to move here. This data item will try to escape the pipeline. What happens with this data item? Nothing. It cannot move because its subsequent stage is full. So this guy will be sitting there waiting until this stage becomes empty. And it will become empty only after it has moved. Wow. So if your pipeline is fully packed, then data items may need to wait until the subsequent stage cleared. Let me press the button, and things are happening. You see it happening at the same time. Well, we know that we need to evaluate Petri nets one transition at a time, but sort of with a rough approximation, it's how it works. So this is moving, this one disappeared, and now this data item is free to start moving. You will see that it starts moving, and it's done. Does it make sense? So the next, it will be a different pair of operations. It will be choice and manage, so choice. Before we are moving on to the choice, do you have anything to discuss about pipelines? The secret with pipelines is to think about them as flags. The data items are moving along, and the flags are going up, down, up, down, up, down. In a pipeline, if you want to model infinite source of data on this side, so not just a single data item is added and then we observe how it moves, right? But infinite source of data, then there should be a path from here to here. We cannot connect with an arc two places. There should be a transition between them. So this transition, which is added here, fires, and it means that this is the action of arrival a new data item into the stage. And it may fire as soon as the stage becomes empty. So basically, by modeling it like this, you will say that as soon as the stage is empty, it may become full at any time it wants. There is no time associated with transitions. It can happen straight away in a microsecond or picosecond, or it may happen in a year time. There is no notion of time in Petri nets. But definitely it will happen at some point because there is no other way for it to occur. Now here, if you want to represent an infinite consumer which consumes everything. It's very hungry guy, so it eats all data items which arrive there. Then there should be a path from here down to here through a transition. It means that this transition will mean that it's an action which lowers the flag. What does it mean? If the flag is lowered, it means that the data have been consumed, it's gone, and we are prepared to receive new data. So when the token is here, this transition can be enabled, and it will be enabled as soon as the data has arrived into the previous stage. So they call it infinite sink or infinite consumer of data. So it will be an arc going from here down to here through a transition. All right. So it's easy to generalize this model to the infinite source and infinite destination consumer by completing the loop on this side and completing the loop on this side. I didn't do this in this experiment because I wanted to show some interesting effects. The next set of blocks based on choice. The choice structurally looks like this. In the center, we have a place. Before that, in the center, we had a transition. Transition in the center of the operation, it's for cojoin. If you have a place in the center of the operation, then it will be choice or actually merge as well. Right? It's easy to remember. Now, choice is when you have several escapes from a place. So the token, if it arrives here, it may go this way or this way. It's a choice. I have no idea which way it will go. It's mathematics. You abstract away from this. So this, they call it, this is a random choice or free choice. Well, free choice doesn't need to be random. Random usually means that it has some particular probability distribution, that sometimes upper branch works, sometimes lower branch works. It's random, right? But here we can say that we don't have knowledge which one fires this transition or this, right? We just not reading the book. We don't have this knowledge. The system may know it internally, but we don't know about the system this kind of detail. And this, we say that it is a free choice from our point of view. Right? Okay, so we can restrict this choice and make it not free. And this is done later here and there. So free choice is a convenient tool to represent some sort of random number generator or a system where we have no knowledge or don't care which choice is made. We just know that after this state, either one or the other action is possible. For example, if the counter is 0, then take the upper branch. If the counter is 1, 2, 3, 4, 5, and so on, then take the lower branch. If you don't care what the value of the counter is, then we can say that the system may take either one branch or the other branch, depending on the value of the counter, but we are not looking at it. So it's abstraction, we're ignoring it. So usually free choice in models occurs as a result of abstracting away from detail or lack of knowledge. Often takes place in the environment, right? So the environment may be such that we just don't know how it operates. There's a very clever thing sits there, for example, a student, right? And student makes a decision. But the system is a stupid thing. It's an electronic device, and its business is to do one action or the other, depending upon what button the student presses. From the point of view of the model of this electronic system, the environment is incomprehensibly complex, and the system does need to know what's going on in your head. What it needs to know is that when one button is pressed, you do one thing, when the other, you do the other thing. And that's when you model the environment in such a system, you put the free choice. In this case, in my last example, this free choice is the free choice of a person in a free society. There will be something else then, control choice. Control choice, it's, well, let me joke about this. It's a non-free choice of a person in a non-free society. Right. So this is the non-free choice. It's still a choice because the centerpiece is this. It's a place. The token arrives from some net here and placed here, and then either this transition or this transition may fire depending upon the gray area of the network. And the gray area of the model, it's something which is happening outside of our choice. Let's assume that outside of our choice, there is another one, which is made in advance. And this advanced choice sends the token either this way or this way. As a result, when this token, when this choice, the black circle is activated, the token is here. Which transition to fire, this or this? Of course, the one which has received the token from the appropriate branch of the previous choice. So structurally, this is definitely a choice because you have a place and several transitions, several arcs escaping from that to different transitions. So it is definitely a choice from the structural perspective. But semantically, the decision is not made here. The decision is actually made before by the supervisor. So from the point of view of this place, this is not a free choice, it's a controlled choice. It's the actions of a person in a non-free society, for example, or an action of a person who comes to buy ice cream. And in the kiosk, they sell chocolate and vanilla ice cream. But the people who came before him or her, they bought off all chocolate ice cream and only vanilla is left. So one choice is blocked by some previous actions. And as a result, we can only go one way and take vanilla. Right. All right, so that's the control choice. Nice building block. It is frequently used as some form of synchronization. What do I mean by this? Imagine that the choice is made actually here, and at some point we need to slow down our one branch or the other branch up to the moment when the signal arrives from here. Right, so you can use this non-free choice as a sophisticated waiting mechanism. Still, the choice exists, just is in the background or environment. Okay, arbitration. Arbitration is often associated with the problem of be redundant as is a donkey. And the problem goes as far in the history, back in the history as Aristotle, but actually it was French philosopher Jean Buridan who became famous for this problem. He formulated it with donkeys in mind. And the idea was that you put a donkey between two bales of hay and balance the system. Make sure that the distance from the animal to one bale of hay is exactly the same as to the other one, and hay is equally attractive on the left and the right. And the hypothesis was that this animal will sit and will try to make a decision, but it will never decide which way to go because he's torn or it's torn between two options which are equally attractive. And the donkey eventually dies of hunger. Right? No animals were hurt in such an experiment. It was just a thought experiment. But apparently it's possible to cause a significant delay by running this model. Now let's have a look at this. This part is very similar to this one. Basically, the token arrives here, and either this or this transition fires, which one, depending upon the tokens arriving into the predecessor places. But the difference is here. Both threads are active, and there is a race which token arrives first. And the one which arrives first enables the appropriate transition first, and this transition is likely to fire. And the one who arrives second is in disadvantage, of course. However, we have a Petri net here. In Petri nets, there is no notion of time. As a result, it's perfectly possible that the token arrives here, the token is also here, this transition is enabled, but it may be sluggish. For some reason, it may not fire straight away. And as a result, this thread will finish and will put will put a token here, and as a result, this transition will be also enabled. And then we will end up with two transitions enabled, similar to this situation. And at this point, it will become a free choice. Random resolution of the choice will happen. So it is designed to decide who is first. Therefore, it's called an arbiter. But if the arbiter faces a very symmetrical problem that both competitors have arrived to the finishing line at the same time, then the arbiter just tosses the coin and randomly selects one of them. Something like this. So this is in gray. This is the indicator that both threads were launched. So for the arbitration choice, it is important that both threads are competing against each other, and the decision is made by this token inside this place in the middle. The token may go one way or the other. So this is used in mutexes, by the way. We'll see the model of mutex next. 1, 2, 3, and apparently there exist more building blocks, but I don't want to talk about this one. It's a confusion, and it is a confusing building block because it's quite difficult to imagine a piece of hardware or software which implements it. Sometimes mathematicians arrive to this kind of confusion structure. A confusion is when they have a multitude output transitions like this, and a multitude of places connected to those, and multitude of tokens in them. And then it becomes quite difficult to decide which one will be firing. I'm not looking at this because it is not practical, we don't need it, but the word confusion may happen, that you will see it in any literature. It may happen in literature. So if you read. Confusion should be refined for implementation as arbitrated choice. So. Right. The next is the model of the device. So it will be using this kind of operation. It will be arbitration. Okay, where is this choice here? That's the choice place, right? And these two threads are concurrent. They're racing, and potentially they can put a token here, here, and then this token will be torn between going right or left, and this will be the arbitration situation. But in general, which thread delivers the token here first, it wins the arbitration in general. I'm saying in general because in this particular case, in the mathematics, we have no notion of time, And if a token has arrived here, it doesn't mean that this transition will fire straight away. It's perfectly possible that it will happen after half an hour. And this half an hour may be enough for this transition to fire and deliver a token there. And then it will be a symmetrical situation. And the arbiter will have to somehow decide at random which way to go, and then it will be a free choice situation. Now, the arbiter includes two loops. One loop here, the other loop here. Indices 1, 1, 1, 2, 2, 2. So this is process number 1. This is process number 2. In each process, we have request, grant, and done. So request, what does it mean? Request event happens. Request to the arbiter to operate. In fact, we are requesting access to a shared resource usually. Right? The shared resource is two processes, right? And both of them want to access a common buffer or a common interface. And if both of them access the same interface and try to output data there, then the characters will mix. So from one channel, we are sending a text, a poem. And from the other, character by character. If both of them are writing this and printing on the same piece of paper in the printer, it will stop being a poem because characters from one poem will mix with the characters from the other. They're not even words. We'll lose any kind of coherence. So we need to first do the job with the first poem and then print out the second poem. That's the idea. So it's one or the other. So this printing of the poem, it's this place. I drew this and this in fat as a large circle. It's not because it's a different kind of a place, it's just the same place, just highlighted as the place where important things are happening. Printing of the poem or accessing the shared resource. And the idea is that we must not put a token here and here at the same time. So it's either here or there, but not in both at the same time, which means that it's here, it means that this thread is printing its poem, then the token is gone from here and the token is placed here, then the second thread is printing its poem, and the words do not mix and the characters do not mix, and the meaning is not destroyed. Now, how does it work? The request fires, and then the token is here, and we are about to fire the transition known as grant. Grant means that you're allowed to start printing your poem, right? And D for done. Done is needed. Why is it needed? Because once we have finished accessing the resource, we need to tell the arbiter that I'm done. So the second party could operate. Therefore, it is request, grant, done, arbiter. Now we are prepared to observe how it works. At the beginning, both processes are doing nothing, they're sleeping. Well, these two transitions are enabled, and I have no idea when these processes decide to wake up. One of them wakes up like this, the first one for some reason. And you see this transition becomes red, enabled, and it's prepared to fire, and it fires. It takes the token from the arbiter. ME means mutual exclusion. Mutual exclusion or mutex means that it's either one or the other, but not both together. Choices. Mutual exclusive choice. Now this transition is red hot, it's enabled, and its purpose is to return the token here once we are finished. Right. The token goes away from here, and at the same time, this place is marked. Now this place is again prepared to operate the grants. What happens next? Right. This request is very fast. Now we have both requests pending. Both grants are enabled. Which one fires? I have no idea, because now we have the symmetrical case, free choice. Without any particular reason, the left one fired again, and this one became disabled. So this one has to wait. It's not fair. I understand. Arbiters are not fair. Now this one fires. And now this one fires. Now we are back to the initial station, so we can continue operation. Does it make sense?
Yep.
Yep. So far, so good.
Yep.
Right.
Yes.
The remarkable part about this model is that if you count the number of cycles in this cycle and this cycle, you will never be able to use these numbers of counters to verify the system. For example, it's perfectly possible that the first process always gets grant and the second never gets. Why? Because we don't have notion of time in Petri-nets. And it will be correct operation. If the second process is broken, just burned, power supply doesn't work or something like this, right? And just the first process is operating. By observing its operation, you will never be able to tell whether it's a broken system or not. It's perfectly possible that one guy always takes precedence. This is why I'm saying that arbiters are unfair. They're fundamentally unfair. Unfairness means that you cannot guarantee that the action in one particular thread or process will take place after a bounded number of actions in the other. So this transition, grant 2, may fire in this particular kind of model after unbounded grant 1 transitions. Unbounded means that I don't know how many of them will be. Can be 10, can be 100, 1 million. So we have a very good decoupling on the left and right. Very interesting model. Very difficult to verify. In order to verify such a model, you need to slow down one thread and observe the other one operating. Then slow down the second one, observe the first one operating. Then you will test. They call this part a critical section in between. The critical sections where one party or the other party can access the resource, not both together, just one at a time. It's a critical section. Otherwise known as request grant done arbiter. Mutexes exist in software implementations. We will look at them. And we will have operation mutex lock for here, for grant. We have mutex unlock, and there will be a variable whose name is mutex. It will be initialized into full position. Mutex lock operation can operate very fast or may cause waiting. So nobody knows how long it takes to complete this function. The operation mutex unlock is always fast because it just puts the token there and that's it. In general, what the arbiter does, it slows down one or the other thread of operation or process in order to achieve a goal of allowing just one process at a time into the critical section. Okay, so what we saw here, it was fork join operations, choice merge operations, pipeline for the first example, arbiter Petri-net for the second example. Any questions about this? While waiting for questions, I can open another set of slides so I could start torturing you with my own questions. Instead of opening, I open the preview, sorry. Examples. Examples, it's you're supposed to be doing it. Should we do them together? At least we can start together. So the first problem to solve. Two pipelines joined together. Okay, the system has two input and one output channels. Each input or output are pipeline's capacity 2. Each input has an infinite source of data items. The output is connected to an infinite sink. Sink, it's the infinite consumer. Infinite consumer for the data items. And the clarification, a single output data item is produced when one item from the first and one item from the second pipeline join. Right. And after that, there is another one. So this is just a specification to a worked example. Have you done those?
Not yet.
You did?
Oh, no. We haven't done it.
Haven't. What should be the approach? What do you think? If you started this, so the approach is to read first bullet points, right? And start with how the problem is described. The system has two input and one output channels, and each input or output are pipelines capacity 2. So we need to draw 3 pipelines capacity 2. Can you draw it for me, please? The pipelines were drawn. I had a capacity of the pipeline capacity 4 before, right? So let's draw those pipelines. Just give me a second. I need to share my other device, my tablet, says that is not a host. How to make it a host? I need to make myself a host. Okay, now I'm together a host and co-host. Let's start drawing things. Share whiteboard. All right. We need to draw the pipelines first. Pipelines capacity 2. I didn't say capacity 10 because I just wanted to minimize drawing. We have 2 input and 1 output pipelines. So I will draw the input pipelines here, and the output pipeline will be drawn there. So the idea is that the data items will be coming somehow and getting through. But the pipelines are identical. So capacity 2, place. They are empty. Something like this. Right? And I need to draw several of those, right? Place, transitions. Sorry for the drawing. It's not fun to draw on a tablet. And the third one is here. And all of them are empty. You see the tokens are below, so the all flags are below. So these are 3 pipelines, 2 input pipelines, 1 output pipeline. And the idea is that the data items arrive in the first and the second, and they do joining. So a data item arrives from here, and only then the output is formed. Right? The data items, of course, they go slowly through this pipeline, and then only when they're at the output, they do something magical, and together with this one, they will activate the output pipeline, right? So it's quite clear that I will have to add the solution somewhere to this area. Does it make sense? What solution? I know that this transition will fire when the data item has been placed here, right? I know that this transition will fire when the data item has been placed here, right? And as a result of firing these transitions, I want the data item be placed here, right? Which makes me look at this transition as well. So basically, the action will involve, I need some other color. This will involve these stages becoming empty and this stage becoming full in no time whatsoever. And my hypothesis here is that for this we need to, it's a bad drawing. Why is it bad? Because I'm connecting together those transitions. Basically, I'm pretending that this is all the same single transition. And this red transition will fire when the token is here, when the token is here, and as a result of firing, it will transfer this token over there. Does it make sense? I think it does, should make sense. And now I can beautify the drawing, stop drawing ugly transitions and make everything beautiful. For this, let me erase this part, and this part, and this part, and replace it with the same transition, This transition will make this stage full. It will make the stage full, and these stages will be made empty through the same transition. So the arc will go here, and from here, here, and from here it will go here, and from here it will go there. That's it. So now this transition at the input, this one, it's the infinite source of data items. As soon as the stage is empty, it becomes full. Right? So it's the infinite source. The same as here. This transition is the infinite source of data items. As soon as the stage becomes empty, becomes full. Right? This causes the stream of data items flowing this direction, and as soon as this stage becomes full and this stage becomes full, this transition fires, this stage becomes full, and this propagates to the output. Does it make sense?
Yeah, so far so good.
Good, good. And those for whom it doesn't, please shout, because I'm going to raise it. Almost close the session. All right, so there are other examples. So, and they disappeared from here. Why are they gone? Exit full screen. Oh. 2 pipelines merge now. Join means that we are taking a token from one input, a token from the other input, and produce a single input to the output, right? And 2 pipelines merge means that one input, for example, is frozen, and the other is receiving the flow of data. And these data are appearing at the output. And if both channels are receiving the data items, then the output produces the combination of whatever arrived from the inputs. So 2 pipelines merge. The system also has 2 input and 1 output channel, so the same setup. Each input or output are pipelines capacity 2, the same. Each input has an infinite source of data items. The output is connected to an infinite sink. So it's like in the previous example. The difference here, a single output data item is produced for each item from either input, i.e., the number of output items is the sum of the items coming from both inputs. All right. So basically, it means that the output pipeline should receive something and its input either from one or from the other channel. Either or looks like choice. So there will be choice involved. Now, what kind of choice? We have no idea how these inputs are synchronized. Actually, they are not synchronized. Therefore, looks like there will be a race condition. So it looks like there will be arbitrated choice. Does it make sense? So when thinking about the specification or thinking about the solution, first we identify the concepts. What does it sound like? I'm not sure at the moment whether all concepts are formed, but the key concept is quite clear. It's either or, which means that there should be choice, and the inputs are not synchronized, therefore, and concurrent at the same time, so they are giving us the race condition. So let's start the whiteboard for this. Again, black color. Again, one pipeline, the other pipeline, the output pipeline. Many arcs. Many arcs. Low quality drawing. Sorry for that. Okay, fat dots, which do not very fat, but sort of they're still dots. All flags are down. Okay, so I prepare to start drawing. So it looks like the solution again should be sitting somewhere here in between those pipelines, right? And there should be choice. It's either one or the other. So there should be a choice. And the choice for us, it is something like this. It's a choice, right? So there should be a place which makes this choice. So we need to put here the data item either from here or from there, right? We are putting the data here after either this or this transition has fired, right? This is done by firing this transition. So it means that this transition is sometimes the same as this one, or sometimes it is the same as this one. So it means that this transition has two faces. It's two-faced, double-faced Janus. So how to deal with this? Let me erase it and replace with an equivalent system where this transition is split in halves. Instead of one transition, I will have two transitions. It's either one or the other fires, and this token goes up. Does it make sense? So it is equivalent transformation. I didn't add anything. I just replaced one transition with two transitions, and it's either A or A. It's kind of tautology at the moment because these transitions are roughly the same, but they're split. So if I add something to this drawing, I can start treating them as different semantics. So it will be either A or B, and A and B both together, they represent the complete set of functionality. And now I will be firing one transition. Actually, I should change the colors a bit. Let me draw this transition as red, and the other transition as green. Right. And now I'll be firing the green transition when the data has arrived here and executed this one, right? And I'll be firing the red one when the data have arrived here and fired this transition. Okay. So for this, I need to remove this, and the condition for firing the green transition will involve the data here. Doesn't happen. Will involve the data there, right? means that it will be something like this. It's supposed to be an arrow. And for the red one, it will be the other channel. The same, just the other channel. So it's either one or the other. Is it possible that the green and red fire at the same time? No, it's not possible. Why is it not possible? Because here we have arbitration. This token will go one way or the other, but not both together because it's choice. So the arbitration operation happens here. So you can call this place as mutual exclusion place, mutex. Does it make sense? So I was trying to talk much because the idea was to deliver the reasoning behind construction. You can see the answer to this example in the recorded talk, I think. But more important is to somehow listen to the way how I am thinking when solving the problem. Does make sense?
Yes.
Right. I'm going to erase this. Please shout if you want to discuss this further. No shouts. All right, we can carry on with this, right? Instead of carrying on, I can ask you actually to look at this. It's basically very similar to the previous example. The difference is that two pipelines merge, still merge like before, but merge in turn. So first we propagate the data item from the first input to the output, then from the second, then from the first again, then from the second again. So taking turns. How would you approach this? Any ideas? So it looks like this behavior is very similar to the previous example, right? But it is more restricted. It's easy to draw things which are more restricted because you take the previous model and add restrictions to this. Restrictions are new arcs. Why are they restrictions? Because the arc has two ends, and if it is pointing at a transition, then the previous end, the left end, will be a place, right? And if there is no token there, then the transition will not be enabled. So basically, you are adding more conditions for a transition to fire. So it will not fire that frequently. So it looks like the solution to this problem will use the solution to the previous one. Just you will have to add something. And what we add to this is a serializer or a sequencer. And the sequencer will do what? It will select the first channel first, or the second channel, the first channel, second channel, first, second, first, second, first, second, first, second. How to do that?
Maybe placing the token at different time, different
Maybe.
distance. Yeah.
Maybe. I suggest the following switch to black color. Take the previous model and add to this a sequencer. And the sequencer will look like first, second, first, second. There should be something which resembles two places, right? First one is marked. That's the sequencer, right?
Yes.
Something like this. So this thing should be added. So these transitions, here there are small transitions, but in our solutions they will become bigger. Why? Because they will be sharing their duties with some other transitions in the previous example. You remember those green and red transitions, right? So these transitions will be adding the preset and post set to those. So it will be something drawn between those red and green. So remember those red and green, how they're drawn. There was red, there was green somewhere. They had their own connections, right? I don't care about those connections. And what I care about now is my sequencer. And the sequencer will be selecting first what? Green, and then red, and then green, then red, and green, and so on. So these are words, and this is a hint. I would like you to draw the solution yourselves. It's your exercise. Nothing replaces an exercise. I can do whatever exercises you want me to do, but as a result, I will improve my own skills and understanding. I would like you to do those. Please try it. Okay. So please do it yourself. So 3 examples were considered. The last one it's you are doing, right? The first 2, please review and solve it again, just to refresh in memory how it was done. Please do not copy from what I said because it makes no sense. And 3 examples are about fork and join. Actually, so what was used in those examples? Fork and join blocks used, pipelines used, choice and merge blocks used in the arbitrated, and controlled choice. Okay, so it's all there. Controlled choice, it's the last example. So instead of arbitration, we are doing the control thing, because we can guarantee that the sequence between the transitions, there is no randomness there. So the next is to start looking at a different topic, which is reachability graphs. And I hope you did have a chance to open the topic. Did you have a chance? No? Yeah, not shouting straight away, probably did. With the reachability graphs, I have something drawn by hand here, because I found it was easier like that. Please open it. So basically, you need first to review what those reachability graphs are, and then go through the sequence of examples. And the examples go from very simple to more and more complex. So just open and have a look first. And the idea is that the reachability graph represents each marking in the Petri net as a state. And as a result of this, if a Petri net has no concurrence, and there are such Petri nets, if you don't have fork and join, it will be just a non-concurrent Petri net, then its reachability graph will be isomorphic, so shaped exactly the same as the Petri net. So no concurrency, isomorphic mapping. If there is concurrency, then the mapping will be funny. What does it mean, funny? It means that the initial marking is a state, right? The final marking is also the state, but in between there is concurrency. So we don't know how we fire A and then B, or first B and then A. Therefore, moving from the initial to the final mapping, we can execute A, B, or B, A. So in case of concurrent transitions, we'll be always getting shapes of the reachability graphs, which look like diamonds. So in reachability graph, each marking like this also here. Marking is a state. Marking is a state, right? And then from this marking, we go to one or the other marking. So transitions are like this. So reachability graphs are finite state machines. So there are no transition. The transition is an arc here. So in case of concurrency, the initial marking, so dot dot, you see, it's this state. After that, we fire first A, for example, and arrive to this intermediate marking. This is this state. After A was fired, the token sits here in this thread, has nowhere to go. We have to fire B. B fired, right? B fired. We are arriving to this state. However, if we fire B first, then this will be this diagonal marking. It will be this state. You see marking 2, state 2. And then fire A, and this end goes down. We are arriving again to the same final marking. So basically, we are departing and arriving to the same thing, just taking different routes in between. Why different routes? Because of concurrency. What's wrong with concurrency? Concurrency executes things in one order, such as A and then B, or B then A. And reachability graphs capture all these behaviors. So these are very, very rich models, very interesting models. And they show how complex your system is. So this system is not very complex because its behavior is roughly of the same size as the original model, right? In this case, well, there is not much concurrency, but still the size of this thing is quadratic with regard to the number of threads, right? So, and then we will see that in some other cases, it can be a cubical 4th degree. And so it's basically becoming, with regard to the number of threads, the complexity of our reachability graph becomes exponential. Oh, case by case, please go then through case by case. So it's the same as before, just instead of A and B, we have longer threads. See, A, C, so 2 steps here, 2 steps. This small diamond becomes shaped like this. Still a diamond because we are departing from the initial marking, arriving to the final marking. But between them, there will be many intermediate states which enumerate in a very regular way, by the way. You see this labeled as A, B, 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 and so on. In a very regular way, everything is labeled. It executes those transitions. Why there are such diamond shapes? Because by firing A, for example, by firing A, you are not affecting B because this part of the graph is completely different from this one. So after firing A, you are under no obligation to do something with B. B could be fired here, therefore it can be fired there. After A, you can fire C, but don't touch B, right? So B is independent from this dimension A and C. So from this A and C, B is completely independent. It was enabled at the beginning and it's enabled in each state. This is why we are labeling all diagonals in a very regular way. And you can repeat the same reasoning for each of these symbols, A, B, and C, and D. But as for A and C, yes, there is a sequence. So C can only happen after A. Therefore, we have A, C, A, C, A, C everywhere. So what I want you to do here is to go through these examples and understand them by checking how you understand. You just draw them and see how these labels work. And they are drawn in such an order that first we have no concurrency whatsoever, and the conclusion is no concurrency, the task is trivial. The new graph is isomorphic to the previous one, right? If there is concurrency, then we are getting diamonds. If each thread is longer than one transition, then each edge of the diamond becomes longer. And if we have increased number of concurrent threads, then we are going from one-dimensional to two-dimensional to three to four-dimensional and so on figure. And after we have digested this, we will be able to solve such problems. We have, for example, 3 threads, and the transitions D, E, and F are controlled by the mutex. So only one of them may happen. Draw the reachability graph so you could explore the behavior of the system. And apparently the behavior of the system looks like this. It means that we are departing from the initial state, which is this marking, and arriving eventually to one of these states, this, or that, which correspond to the tokens being placed here, here, and there. You see that when the token is here, then this transition, these are fully blocked. Therefore, the tokens in the other threads, they're frozen here and there. So we are arriving to a system which has one kind of initial positioning of the tokens and may have 3 different outcomes as a result of execution, and then it stalls. There is no cycle here. It has the initial state and 3 final states. And this is a 3D picture depicting a 3 parallel a system with 3 parallel threads. So I would like you to go through this and tell me eventually how it went. Okay. So reachability graphs are quite kind of useful to in understanding of complexity of the problem which you are solving, because they explicitly enumerate all states in the system. Take an RGD arbiter and draw a reachability graph for it, and you will discover that this arbiter is very unfair. Why? Because it will have an edge in this reachability graph, which is infinitely long and does not involve giving grant to the other party. So this is an important conclusion. You want to have arbiters fair, judges fair in the court, right? But sometimes it's impossible. Apparently, in presence of free choice, it's impossible if there is free competition. So there will be always an element of unfairness. And this will be seen eventually in the experiments with software, by the way. So after that, we will start our software experiments. And somewhere here, concurrent programming. When talking about concurrent threads, in this set of slides and this talk, we will see an example where our concurrent threads show the effect of unfairness. So we have two threads. One of them is printing on the screen 1 1 1 1 1. The other is printing on the screen 2 2 2 2 2. You launch the system, and instead of seeing on the screen 1 2 1 2 1 2 1 2, it just fills the whole screen with ones all the time. Right? This means that this event of unfairness is taking place. So it is important kind of experience to see that it may happen. So you're assuming that if things are random, then it will be a mix of outcomes. But this free choice situation, lack of knowledge, rather than randomness with predefined cross-correlation or auto-correlation properties. It means that sometimes it is just stuck in one particular position. Okay, so the next we'll be talking about software. Next we'll be talking about software, and please finish your descriptive and systems and start looking at these lectures about software implementations. The software implementations of finite state machines, it's a very simple topic. Please do it yourselves. There are several ways, standardized ways of implementation. And, the concurrent programming is slightly more complex, and probably we need to talk about this, and I will demonstrate things. You can type it on the terminal and have all those experiments running for you. I'm providing also the examples for the concurrent programming, and the examples are somewhere here. Code used in lectures, try it at home. So I can always log into Unix Newcastle ACUK, or if you're running Linux at home, and just compile and see how those examples work. So this should be done together with the lectures. Please do not neglect the lectures, go through the lectures, and as for demonstration, discussion of examples, this is what we are going to do. All right, any further questions, please? Nothing. In which case, should we call it a day? And then I'll see you tomorrow. Thank you for coming.
Thank you very much.
Thank you.
Yeah, thank you.
Thank you, Professor.
Thank you.
Thank you. Bye.
Thank you.
Bye-bye.
Bye.
Bye.